We are going to discuss single conversion transponder or bendpipe type of transponder that is used in C band or 6 by 4 gigahertz band. So this is the block diagram of the basic block diagram of the transponder. So let us try to understand the functionalities of this particular transponder. So here we have 6 gigahertz uplink antenna. So this antenna will intercept the signal coming from the ground station at 6 gigahertz. After interception, the signal must be very weak signal, right? So that signal must be amplified first. Otherwise, we cannot perform any operation on it. So for that, we use low noise amplifier. Now, why we have to use low noise amplifier? Because low noise amplifier will produce minimum amount of noise, and obviously it must have very high gain, right? Now, very high gain and low noise figure, these particular characteristics will ensure the overall noise figure of this whole system. The first stage of any receiver must have very high gain and it must generate very small amount of noise, right? So after low noise amplifier, we have amplified signal, but that amplified signal may contain some other frequencies. So we must have some band pass filter. Well, this band pass filter may also be incorporated in the low noise amplifier. We are just showing it in the separate block. So here we have 6 gigahertz signal. This 6 gigahertz signal must be down converted to 4 gigahertz. For that, we use a mixer, and the another input of this mixer is a local oscillator at 2225 megahertz frequency. Okay. The output of the mixer or the down converter will be the sum frequency and the difference frequencies. At the same time, since it is a nonlinear medium, it is a nonlinear component, so some other frequencies may also be generated, right? But our required frequency is the 4 gigahertz, that is the difference frequency. So for that, we use this bandpass filter at 4 gigahertz to ensure that other frequencies are removed and only 4 gigahertz is now passed. Okay, so at this point we have 4 gigahertz signal. So 6 gigahertz information is now converted into the information is the same. The carrier frequency is now 4 gigahertz, right? Now we have low power amplifier to actually to improve the amplitude of the signal, and then we have high power amplifier to enhance the power level at 4 gigahertz, and then the high power signal is passed to the downlink antenna at 4 gigahertz to transmit it towards the uh, ground station, right? So this is the overall functionality of a single conversion transponder. Now, why this two frequencies are different, right? See, uplink frequency is 6 gigahertz and downlink frequency is 4 gigahertz. They are not same. They should not be same to avoid the interference, right? If they are using the same frequency, then there is a chance of interference. So same frequency cannot be used. That is for sure. But why? The uplink frequency is greater than the downlink frequency, right? So first of all, it is easier to generate higher range of frequencies at the ground station because ground station composed of huge amount of resources, right? And satellite is actually limited resource, has limited resource. So it is easier to generate the 6 gigahertz signal at the ground station. Not only that, the ground station antenna must have very high gain because it must point towards the satellite, and it should not, its beam should not be intercepted by the adjacent satellite, right? So beam must be narrow enough. To make the antenna beam narrow enough, it requires huge gain actually. Antenna gain of the ground station transmitter antenna must be very high, right? Now, if we use higher range of frequency, then the same antenna will provide larger gain. Okay. So if we use higher range of frequency for uplink, the antenna gain of the ground station antenna would be high. For that, higher frequency is used for uplink, right? Not only that, it would be easier to down convert the signal. So if we use 4 gigahertz right here and 6 gigahertz as downlink, then we have to use some kind of up converter, and it is difficult, comparatively difficult, to generate up converted signal. That is, if we instead of using the difference frequency, if we use some frequency, then that will be of less power. Okay, some frequency will have lesser amount of power and it is difficult to generate. So instead of that, if we use 6 gigahertz as uplink and 4 gigahertz as downlink, we can easily use conventional down converting technique, and we can easily generate 4 gigahertz signal at high power level. Okay, now what happens to the downlink antenna? See, if we use the same antenna for 6 gigahertz, the antenna gain, this particular antenna gain would be higher, definitely. But since we are using 4 gigahertz, the antenna gain for this particular antenna would be lesser, right? That is correct. But point is, why do we require lesser gain at downlink antenna? Because for downlink, what is the objective of this downlink? The downlink objective is to cover a wide region on earth, right? It is not a pointed region. It is not trying to contact with a single point. It is trying to contact, or it is trying to uh, broadcast broadcast over a wide region, right? So we don't require very high gain for downlink antenna, right? That is why if we use 4 gigahertz frequency at downlink, the same antenna will work. The same antenna will work because the objective of the downlink is different from the uplink. Get my point? For uplink, it has to be pointed towards the satellite only. But for downlink, it is not intended to contact with a certain point. It is trying to broadcast it over a region of space on Earth. So obviously we don't require high gain antenna. Okay, so 4 gigahertz will work. Now we'll try to understand the double conversion transponder that is used in Ku band, that is 14 by 11 gigahertz band. Here we have 14 gigahertz uplink antenna that will intercept 14 gigahertz signal. By convention, we have to use low noise amplifier, right? First stage must be low noise amplifier. So it will amplify and it will eliminate some out of band signals as well. And then we have 14 gigahertz band pass filter. So only 14 gigahertz signal will pass. We have first down converter or mixer, and another input of the mixer is 13 gigahertz, and that is generated with the help of local oscillator, right? So what will be the frequency at the outside, at the output of this down converter? Lots of frequencies will be there. We have to choose only the difference frequency, right? So 14 gigahertz minus 13 gigahertz, that is 1 gigahertz is the difference frequency. So that difference frequency must be passed through this bandpass filter, So here we have 1 gigahertz signal. Then we have 1 gigahertz IF amplifier to amplify the signal, and then that is given to the up converter, right? Because it is 14 by 11 gigahertz. So we first down convert it into 1 gigahertz, right? In IF stage, and after IF stage, we have we have to increase the frequency, right? To increase the frequency to 111 gigahertz, what we have to do? We have to have another uh, mixer with 10 gigahertz of local oscillator. Okay, 10 gigahertz of local oscillator. So mixer will produce a sum frequency of 1 gigahertz plus 10 gigahertz, that is 11 gigahertz. That 11 gigahertz signal will be given to the bandpass filter. That bandpass filter will eliminate other frequencies and it will allow only the 11 gigahertz. Then we have 11 gigahertz high power amplifier. The amplified signal will be uh, transmitted via 11 gigahertz downlink antenna. So that is the function of a double conversion transponder. Okay. Onboard processing transponders are actually used in nowadays. They are actually using digital technology, and it has different kind of uh, flexibilities. And obviously they are exploiting new technologies, so obviously their performance is better. So what happens, this is the multiple beam uplink antenna is there. Nowadays it is available, this type of antenna is available. Then we have the basic receiver, right? Then we have the demodulator. Then we can apply some decoder for forward error correcting code, because during transmission some errors may be there. So if there is any error and it is found that some error is there, then we should not go back to the transmitter again for to requesting for retransmission. Rather, forward error correcting code will generate the uh, actual information. That means it will try to correct the code, right? So then we have baseband processor, and we have some onboard controller, because they are exploiting digital technology. So we can have this type of system. Next, we have to transmit it back um, towards the ground station. So another forward error correcting code may be applied. Then we have the modulator. We have already demodulated it, right? If you can remember, in bent pipe type of system, we never demodulate the signal, right? We just down convert it, right? But here we have the uh, demodulator right here, so we have to modulate it, right? So after modulation, we have a transmitter composed of filter, amplifier, etc. And we have some kind of onboard controller, sorry, on the antenna which is controlled by onboard controller, because we have multiple beam, right? And we can switch the beam in which direction the signal will go. That will be decided by the onboard controller. Okay, so we have to assign the particular beam for that particular signal. So all these things are possible nowadays. So onboard processing may also be used to advantage to switch between the uplink access technique and the downlink access technique, so that small earth station may access each other directly via the satellite. So the processor can provide the data storage needed for a switch beam system. So obviously this is advanced technology. They are exploiting advanced technology. And in previous days, this technology was not there. Nowadays, these technologies are there. So these type of transponders are used nowadays.